Hello guys, Jim Malis again. Let's do chapter 5. It pertains to Newton's laws of motion. We've already discussed that in earlier videos. We've got enough background that we do some of these problems. These problems, a lot of the problems themselves and a lot of the content all comes out with time, with hard work, with reading this stuff. Even within the context of solving the problems, when we solve these problems, it's a lecture in its own right if we're showing what it is that we mean with what we're doing. Hopefully I've given you some background that's good enough for you to start with this. Always be reading the book on your own as well, guys. I mean, as we're doing this right now, hopefully this material is useful to people in the near immediate future, but hopefully in somewhat at a somewhat later time, when the health crisis is not what it is, and hopefully things are much better. Hopefully this can still be of use to people that might want to look at this stuff, you guys. Chapter 5 pertains to Newton's laws of motion. We've got the background to do it. We've got the background to do it. Now we're simply going to do it. The problems that we're going to do, and I've already kind of started right here with a particular problem. I started with problem 11, but it's going to be the problems are going to be from chapter 5 that I'm going to do right now live. Somewhat live, right? The problems from chapter 5 are going to be 11, 23, 47, 68. And so that should be okay. Now, for problem number 11, they're saying three forces act on an object with F sub 1 vector equals the quantity. Three forces act on an object with F sub 1 vector equals the quantity 6.03i minus 10.64j. That's this guy. That's one of the vectors. The other vector, they're acting on an object. There's three vectors acting on an object. One of the vectors is 6.03i plus negative 10.64j in newtons. That's F sub 1, we'll call it. They call it F sub 1, so we'll call it F sub 1 as well. F sub 2 vector is negative 3.71i. F sub 2 vector is negative 3.71i plus negative 12.93j, also in newtons. So negative 3.71i plus negative 12.93j in newtons for F sub 2 vector. And F sub 3 vector, we don't know what it is, but they're saying when you add all three vectors together, the resultant force acting on the object is equal to 0 vector, is equal to 0 newtons. So they're all going to cancel each other out when you add all three of the vectors together. They gave you two of the vectors. They gave you two of the vectors, and you want to find the third vector so that they all cancel out. Again, vectors add like vectors. Vectors add according to the principles of trigonometry, and they add according to the principles of the Pythagorean theorem. The Pythagorean theorem and all the trigonometry that surrounds it are how you add vectors. We've talked about that in excruciating detail at this point. So what do you want to say about it? Well, we could say it's not like adding money. You know, it doesn't matter if the person gave me $20, the other person gave me $30, and the other person gave me $50. It doesn't matter if somebody came from 500 miles north of here, the other person from 500 miles south of here, and the other person from 500 miles west of here. Or it doesn't matter if all three people came from, I don't know, from the upstairs, the fourth floor of the building in which we find ourselves, or the fifth floor, or eighth floor, or whatever floor whatever floor is above us. Let's say it's the 10th floor, and they come right down, and all three people deliver the money. The money's the money. You add the money, it's just a scalar. If I load up a truck with 1,000 kilograms of material, there's not much more to say to that. There's 1,000 kilograms of material in the truck, and in the glove compartment, there's $10,000 in cash. The $10,000, how it all adds up doesn't really matter a whole lot. With vector analysis, sometimes it doesn't matter. Sometimes it doesn't matter. The final answer is the final answer. We get that. When you get the final answer, nothing matters. I get it. But when vectors of particular magnitudes act as they act, the direction in which they are acting also plays a role. And you just can't add, oh, this vector's the size 10, the other vector's the size 20. Let me add 10 and 20 and get 30. $10 and $20 is $30. 10 kilograms and 20 kilograms added onto the same tractor bed, that's 30 kilograms. I get all that. No vectors there. But a vector 10 units long and a vector 20 units long, it depends on what direction they are acting. You have to add them according to vector analysis, according to the trigonometry that we know, according to the Pythagorean theorem that we know. So that's a big thing. It's a big thing. So here we're told there are three vectors. F1 vector, that's this guy. F2 vector, that's the second guy. F3 vector is unknown, so I'll just say I don't know what the x component is. I'll just say it's x. I don't know what the y component is. I'll just say it's y. But when I add all three of these vectors, I get the zero vector. When you add all three of these vectors, you get the zero vector, and these are it. These are the three vectors. F1 vector, F2 vector, that's him. F3 vector, that's him. All right. Well, how does that work? How do you get zero vector? Well, the way that's going to work is if you add all the i's together, they got to add up to zero. You know, the zero vector here, guys, is 0 I hat plus 0 j hat. Yeah, okay, great. Well, how are you going to do that? Well, let me add all the i's, all the I components, all the x components. This and this, when you add them together, positive 6.03 and negative 3.71 is, I think it's 2.3, I think it's a positive 2.32. I'm just doing this in my head, guys. Let me look at it. It's actually, let me see. Yeah, it is a positive 2.32. So you add this and this and get a positive 2.32 plus x. So 2.32 plus x, that's I hat. And then the other one is add this and you get negative 23.57. So that's negative 23.57 plus y. That's j hat. Well, let's get it straight, guys. I mean, what's going on is 0 I hat is equal to this, and 0 j hat is equal to this. 0 has got to be equal to that sum. 0 has got to be equal to that sum. Correct. And 0's got to be equal to this sum. Add a negative 2.32 on each side. X equals negative 2.32. Add a positive 23.57 on each side. Add a positive 23.57 on each side, you get that. What's going on here? Well, we just got it. The problem is basically solved at that point. F3 vector is x I hat plus y j hat. X is negative 2.32i, and y is positive 23.57 j. So we're looking pretty good, guys. Give me a second. Let me just make sure everything's okay. Yeah, it's fine. So I want to make sure everything gets written down for you guys. You can see it. So that's where they're going. That's 11. Let's talk about 23. '23 is saying the x and y coordinates of a 4 kilogram particle moving in the xy plane under the influence of a net force F are given by x equals t to the fourth minus 6t and y equals 4t squared plus 1 with x and y in meters and t in seconds. What is the magnitude of the force F at t equals 4 seconds? So let's take a look at it. All right, guys. For 23, okay, we said what we said, guys. Let's see where it's all gonna, how it's all gonna play out, guys. So there's a number of ways this can be done. We are, again, for giving the calc-based treatment of 209. We are going to look at this. Let me just see in a good manner to kind of look at it, if you don't mind. Okay. Yeah, I think what we're just going to say is this. In the strictest sense, guys, remember Newton's second law, force equals mass times acceleration. It's a big thing. As we said last time, this does go with our gut feeling. Force equals mass times acceleration. Force equals mass times acceleration. Why is it a big thing? Because in some regards, I could almost dare say that it's obvious. I don't know how many things are obvious, to be honest with you. I've had arguments with people in the past outside of the academic setting, and people have said, "Oh, that's obvious." Well, what's obvious and what's not? I mean, that in itself is somewhat of a debatable matter. In a sense, this has an element of being very obvious in some regards. Why? Why does it do that? Well, okay, everything's vectors, right? M is a scalar, acceleration vector is a vector, F vector is a vector as well. If you want to talk about a scalar quantity, let's ignore the vector aspect to it, and let's just say, hey, look, man, there's an acceleration, it's going in a particular direction. We're going to not worry about that direction. We're just going to say, okay, what's going on? Okay. Force equals mass times acceleration. Yeah, it makes a lot of sense to me. If some object is not very big, not very massive, and I'm giving it an acceleration, I'm changing its speed, not by much, and I'm taking my time to do it. I'm not giving it a real strong jolt. If I'm changing the speed not by much and I'm doing it really slowly, and it's not a very massive object, that doesn't require a lot of force. If something is very massive and it gets jolted very violently, if there's a great acceleration and a great mass, that pertains to a great force that would have to accomplish that. There's no small force that's going to generate a great acceleration on a massive object. There's no small force that will do that. So force equals mass. The force that is being applied, that is experienced, I could say being applied, maybe better, maybe easier way to say it. The force that is being applied is mass times acceleration. The force is directly proportional to how massive the object is and directly proportional to the acceleration that it's going through. Great acceleration and great mass had to be a great force to have it happen. They are telling us, they're basically trying to tell us what is, okay, the way this is kind of put, I'm almost putting the carriage in front of the horse on this one, but let's see how we can say this. Let me read this again. I think it's worth our time to read it again, guys. I just don't want to do the problem without reading it for you. even again if I have to. The x and y coordinates of a 4 kilogram particle moving, the x and y coordinates of a 4 kilogram particle moving in the xy plane under the influence of a net force F are given by x equals t to the fourth minus 6t. So let me see here. I'm just going to write it. I'm going to go a little bit off my notes here. X equals x equals t to the fourth minus 6t, and y equals 4t squared. Obviously there's a j hat here, and here there's an I hat. Okay, so what's going on here, guys? The x and y coordinates of a 4 kilogram particle moving in the xy plane under the influence of a net force F are given by x equals t to the fourth minus 6t, and so x equals t to the fourth minus 6t and y equals 4t squared plus 1, with x and y in meters and t in seconds. What is the magnitude of the force F at t equals 4 seconds? It's kind of a weird thing they did. When they give us this information in the book, you guys, they basically write it like this and kind of leave it at that. And then for this one right here, they also write it like this and leave it at that. There's nothing wrong with what they did. In fact, I wish sometimes things would get done like this a little bit more often sometimes. I don't mean just in this book, but in numerous books. Wish I would do things like this a little more often myself, to be honest with you. Here's the thing. They gave you this in terms of scalar, in terms of magnitude. These are, in a sense, these are scalars because they didn't put a vector symbol on them. We know that there is something going on in the x direction. We know that there's something going on in the y direction. Okay, they already communicated that. They said that here. Yeah, I know. But I also want to say, and perhaps the book could have explained this a little differently. I don't know. I'm not going to make that judgment. Right now, we're not going to worry about it. We're going to just say this. There is an x vector. There is a direction and a magnitude. There is an x vector. And if I put an I hat here, I not only have a magnitude, but I have a magnitude times a vector, which gives me a vector. Here I have j hat, a magnitude, multiply magnitude with vector, I get a vector. This is something to keep in mind. You can't just add this like money. The way they gave this to us in the beginning was like it was money. But it's not. It's this. So, they're asking for the magnitude of the force. And you don't add vectors. You don't add vectors like you're adding money. You add them using trigonometry, using vector analysis, using triangles. They add like triangles. They add like the Pythagorean theorem. They don't add like scalars. Initially, you almost thought you were off the hook when you got this. You've got to write it in terms of vectors because they're both going in different directions. The x value is going somewhere east or west. The y value is going somewhere north or south. You can't add 10 units north with 20 units east. 10 and 20, I know adds up to 30, but if this thing's going up 10 and this thing's going across 20, you're not going to add them together. You're going to add them like you're going to add them like this. Here's 10, here's 20, here's a theta, here's C, and the C is not 10 and 20 to give you 30. You're adding two vectors, but it ain't money. 10 and 20 is 30. That's what I'm trying to say. They almost, part of the part of the challenge and part of them trying to fool you, which is part of the question. It's part of the challenge. You're going to get, you know, part of how they're going to challenge you if you can solve problems or not is, can we fool you? Can you start going here and start adding this way? No. This is somewhere in the X direction. This is somewhere in the Y direction. I may not be clear if it's going north and south. I may not be clear if it's going north or south for the Y direction. And I may not be clear if it's going east or west for the X direction. In regard to the X component, it may be going east or west. In regard to the Y component, it may be going north or south. But I do know they're perpendicular to each other. It doesn't matter where they're going. It doesn't matter if they're going this way or this way or this way, that way. Look, man, when you draw these, here's a triangle. Here's a triangle. Here's a triangle. Here's another, you know, draw here, triangle. Draw here, triangle. Draw here, triangle. Draw there. It doesn't matter. You know, 1, 2, 3, 4. All 4 of these triangles are identical in size. The hypotenuse is identical. So I'll still get the right answer. That's why they were saying magnitude. You're not sure where it's exactly going, but I do know these guys don't add up like money. They don't add up like money. That I know. They add up like this triangle or that triangle or that triangle or that triangle, but they're identical triangles. The directions are messed up, but I do know X components and Y components are for sure perpendicular to each other. I don't know exactly where the orientation is going to go, but I do know that they are perpendicular to each other, and you're not adding 10 and 20 to get 30. You're going 20 squared plus 10 squared. The square root of that sum will give you the length of the hypotenuse. And that's kind of where they're going here. So they're trying to they're sort of pulling a fast one on you. So you got to watch out. So let's see what they got. I mean, this is the game they're talking about, I guess you could say. See how you want to talk about it. Okay, so stay with 23, and let's see what they're going to do. I mean, how are you going to figure out a force vector? Well, I'm not worried too much about the directions as long as I know that everybody's all the I components are orthogonal to all the J components, and that's the main thing I care about. I can draw my triangles. You just saw me. I can draw them about 4 different ways, but they're still going to be the same triangle in this particular case, at least in 2-dimensional space. In multi-dimensional space, it's there's actually an infinite number of triangles you could draw at that point with a particular set of vectors. How that would play out. So what we can say here is, or perhaps maybe not an infinite amount, but there's a lot of ways these things can be done, to the point where there's an infinite amount of ways. If you play the game right, you can get a lot of different answers here. Our concern is we're not worried. That's our concern. We're not worried. It's 4 kilograms. Force equals mass times acceleration. Now I'm going to take a sub x I hat. That's the acceleration vector that way. This is the acceleration vector the other way. So one's east or west, the other one's north or south. And how does that work? Well, I'm still kind of not sure. You might say I'm not sure, but I do know this. The first derivative of x is velocity. First derivative of x or first derivative of y is velocity. The second derivative of either one of those is acceleration. So to make a long story short, take the second derivative of the x vector, take the second derivative of the y vector, and we're not worried too much. I mean, I don't want to, I don't want to like do a problem within a problem, but there are very many ways vectors can be oriented. In that regard, there's an infinite number of ways vectors can be oriented. And you can still, as long as there's some kind of orthogonality going on, I can make, literally, I don't take back what I said earlier. There's an infinite number of ways I can orient things, the way vectors can point. In two-dimensional space or in three-dimensional space and beyond. We're not worried about the beyond. I mean, the two-dimensional, especially three-dimensional space is really the money for what we're doing, okay? For what we need to do in the overwhelming majority of things in everyday life. And some fascinating mathematics pertaining to that. What's going on here? D squared x vector dt squared plus d squared y vector dt squared also. And is there another way we can write that? Yeah. I had. Yeah, that's all it is. You just you take x vector is the same as x I hat. Y vector is the same as, x vector is the same as x I hat. Y vector is the same as y j hat. And you get down to here. Okay, what does that mean? Well, that means just let's take everything we got. I mean, we're assuming here now there's a lot going on here, and the orientation of these things is debatable, as I just told you. It's somewhat it can be debatable, but the actual magnitudes under consideration and the fact that there's orthogonality, that is not debatable, and that's why this works. Okay. Enough said on that. I don't want to keep emphasizing that because maybe a little more harmful than it is helpful at this point. Let's talk about it, guys. You are basically getting the second derivative of the x function, and the x function is you're getting the second derivative of the y function. Sorry guys, I ran out of room for the j vector there, but there it is. Okay, go ahead and do it. Go ahead and do it. The second derivative of the first derivative of this is 4t to the third minus 6. First derivative of t to the fourth minus 6t. First derivative of this is 4t to the third minus 6. The second derivative is 12t squared, period, 12t squared. So you've got 12t squared I hat. And this one right here is, the first derivative of this comes out to 8t. The second derivative of that is the first derivative of the 8t, which is just 8. There's a constant acceleration up there, at least. There's a lot to say here. So let's see what we can say. I mean, we'll say this right here. Bring the 4 inside. Have the 4 come right inside, guys. Four times this is 32j. Bring the 4 inside and do what you got to do. That's in newtons. Yeah, that's great, but I'm not adding it like money. They are orthogonal to each other. It is debatable. This could be negative 48 for all you know. This could be negative 48t squared, and this could be negative 32j. True. or some combination thereof. The first one could be negative or positive. This one could be, this is where I got the 4 scenarios I told you. This could be positive or negative. This could be positive or negative. Doesn't matter. The triangle's identical. The location of the triangle is different. I care about the magnitude of the triangle. The magnitude of the hypotenuse. That's okay then. That's why I drew those 4 earlier. At t equals 4 seconds, you put 4 right here. Remember now, they're asking us what's going on at t equals 4 seconds. Put 4 right here. Put 4 right here for t. 4 squared is 16. 16 times 48 is 768. And there it is. Great. How big is it? You don't add it like money. It ain't going to add up. 768 plus 32 is 800. No, it doesn't work that way. It's going to add up how? You're going to take F is going to be the magnitude of F vector is going to be the square root of the quantity 768 squared plus the quantity 32 squared. 32 squared plus 768 squared. Yeah, add them together, get an answer. Square root the answer, you're done. $768 and that's it. That's all they're talking about, guys. There's some good, and again, there's a whole bunch of other problems, guys. I'm not, it's hard. You see, it's a little bit of a challenge to lecture these at any time, even in the best of circumstances when you're in front of people. You just run out of time. You can do a lot more work, but you got to go a lot faster, and at that point, you're not really explaining as well as you'd like to explain. So you try to find some kind of balance. Do we reach that balance? I don't know. Sometimes yes, sometimes no. We try to reach it, obviously, right? There is a great problem number 47, an excellent problem, and we are about to do it. So this is what we got so far. We did 11 and 23. Let's do 47 and let's talk about it a bit. And there's numerous scenarios, I guess, that play out with this thing. Let me look at it myself while we're at it. I'll look at it again when it comes time to it, to do it. On page 150 of the Katz book, problem number 47, a block with mass M1 hangs from a rope that is extended over an ideal pulley and is attached to a second block with mass M2 that sits on a ledge. The second block is also connected to a third block with mass M3 by a second rope that hangs over a second pulley and is shown. They're all ideal pulleys in this case, guys. If the friction between the ledge, and it's shown in the particular figure that I'm going to draw you guys, the friction between the ledge and the second block is negligible, and M1 is 3 kilograms, M2 is 5 kilograms, M3 is 8 kilograms. Find the magnitude of the tension in each rope and the acceleration of each block. Later on, they get into this thing called friction, and you can do a problem like this if there's friction involved. Not only that, you can get into a problem like this if the pulleys are not ideal. If the pulleys themselves, you got to account for the fact that you got to spin the pulleys. You got to make the pulleys move. Making the pulleys move means that you are expending energy to make the mass that is located on the pulleys. The pulleys are composed of mass distributed everywhere throughout the pulley, everywhere throughout the disc. If it's an ideal pulley, you're not worried about that. The pulley's massless for our purposes. It doesn't have any kind of moment of inertia. Later on, we talk about moment of inertia, and the pulleys themselves have mass. They have mass distributed. It depends how the mass is distributed. You've got to take into account what's going on with those pulleys. Are they like bicycle tires and there's no mass inside them and there's mass on the outside? Are they like discs, like a pulley usually is, and then the mass is, let's say, evenly distributed throughout the disc? You got to account for that because you're going to make that thing spin too, and that creates a challenge. So if there is, if there is a pulley and it's not ideal, and if there's friction occurring as well, friction and moments of inertia make this problem substantially more challenging, but we're going to be able to do it. We'll be able to do it. Let's hit this problem as it is right now and get an idea of what's going on. Okay, so 47 and 68 from chapter 5. Let me just get all of this out of here, guys, so I give myself a little more room. Okay, guys, so they're saying here, find the magnitude of the tension in each rope and the acceleration of each block. How is this all working out, guys? Well, this thing called tension is just a fancy word for force that the rope is exerting on a particular object. The tension in the rope will tell you how much force is being exerted on a particular object. So 47 from chapter 5, you guys. Well, acceleration is a vector. Magnitude of acceleration is a scalar. So we'll kind of figure that out, what's going on here. We got to use our best common sense to figure out what is happening with this stuff, you guys. Well, like I said, we're going to be in good shape down the road. We're going to be able to try to do different scenarios that are going on here. Well, this is a pulley right here. This guy's on the ledge, and there's no friction, though. We're not going to worry about that. M3, let's see what we can say. M3 is basically the most massive of all of these. I think it goes, what did they say, guys? So M1 is 3 kilograms. M2 is 5 kilograms. M3 is 8 kilograms. So I haven't finished drawing it, guys. Let me just kind of see here. M2 is 8. Yeah, M1 is this. Look, our common sense, I'm not trying to be not trying to be too cavalier about the whole matter. Let's see what we can say here. That's M1. I'm making one smaller than the other. I made the middle guy bigger than I should have probably, but let's see what we can do here. All right, guys. Look, I mean, there's always the idea, and I'm not trying to sound... Let me see here, guys. Okay, guys. There's a lot that can be said here, guys. Let me probably say a couple things. Let me say enough about this. I think it can be kind of hopefully helpful to us. There's a lot that can happen here. You could have friction at some point, and we can kind of talk about it. Let me not talk about it just yet, but let me talk about it soon. Everybody understands the most massive of the three masses here. The most massive of the three masses here, you guys. The most massive of the three masses is M sub 3, which is 8 kilograms. The second most massive of the three masses is M sub 2, which is 5 kilograms, and M sub 1 is the smallest in terms of mass of the objects under consideration. So the objects are M1, M2, M3. M1 is 3 kilograms mass, M2 is 5 kilograms mass, M3 is 8 kilograms mass. My gut tells me that the acceleration is going to go that way, is going to go this way, and is going to go up. Got to remember, guys, why am I drawing the same A everywhere? The reason I'm drawing the same A everywhere is these guys are all connected. They're all going to move together. Wherever they move together. So, we have what we have this way. The tension, you guys, is something that's going to stop this thing from moving. Because of Newton's third law, the tension that is exerted onto mass M3, the tension that is exerted this way, we'll call it T2. That tension which is exerted this way also gets transferred and gets exerted this way because of Newton's third law. In other words, somehow, if there is a tension stopping, if there's a tension stopping this guy from going into a free fall, this guy's gonna, if you cut the rope right here, this guy will accelerate downward at G, 9.8 meters per second. 9.8 meters per second. The fact that it's there's a tension stopping it. The tension yanks. Yeah, the tension does yank that way. But to do that, there's a pull this way. In other words, there's always the action-reaction. In other words, for this to happen right here, if this guy pulls down, there's a reaction, there's a tension reaction this way, and it also finds itself right here. Same thing right here. There's a tension right here of T1, but that T1 is also right here. And notice how I made T1 smaller than T2, because there's a tug of war there. The T2 has to be bigger than T1 if M2 is going to move to your right. If M2 is going to, as you're looking at this board, M2 is moving to your right, M3 is moving down, M1 is moving up. There is, see, I'm going to try not to make this, this is M1G. This is M1G. It is smaller than T1. Why would take a snapshot of 3 scenarios. Scenario 1. Scenario 2. And scenario 3, which is hopefully bigger. It looks like it is, yeah. This is M3G. Pretty neat problem in that regard. I mean, it's in other words, it's saying here, that's longer than that. Okay, I guess that's believable. It has to be. If this guy is going to go down, M3G, its weight has to be stronger than the tension acting on it. If this guy is going to go to the right, if this guy goes down, he's pulling this guy to the right. If this guy goes down, he's coming to the right following this guy. This guy goes down, this guy goes to the right following. For that to happen, T2 and T1 have to be of different size for there to be an acceleration. T2 has to be a bigger vector. T2 has to be a bigger vector, you guys. T2 has to be a bigger vector than T1 because the difference between the two means there's a net force going to the right. If there's a net force going to the right, the acceleration will be to the right. If there's a net force going down, because M3G is bigger than T2, there's a net force going down, the acceleration is going to be going down. If there's a net force going to the right, the acceleration is going to be going to the right. Yeah, I want this guy following this guy falling. I want this guy following both of those guys, so T1 better be bigger than T1 better be bigger than M1G. T1 better be bigger than M1G for that to all happen. So what's going on, guys, is essentially, we'll try to use some chalk here. I think you can see it pretty good. All right, guys, so essentially, guys, what we have is, we got that right there. We got this right here. So that's 2. That's 1, that's 2. And this whole thing right here is scenario 3. So you got scenario 3, scenario 2, and scenario 1. Should have used the other chalk, you guys. But anyway, you get the picture. Scenario 1. Scenario 2, scenario 3. What determines that? I'll just put it in plain terms, guys. If there's no friction whatsoever here, this guy can move. He can move a lot easier if he's not very massive. If there's no friction, I got to make something clear. This thing could be the size of an aircraft carrier, and if there's no friction, you can move it. Yeah, but you can't move it with a great acceleration. You need a great force to give it a great acceleration, even if there's no friction. Even if there's no friction, you need a great force to move it with a great acceleration. But you will be able to move it. If there's an unbalanced force, it may move. It may take a year for that aircraft carrier to move 1 centimeter, but it will accelerate, theoretically. If the pulleys are ideal, there's no friction, the whole thing. There's an unbalanced force here, guys. Unbalanced, a lot of stuff. If M3 is the biggest of all the masses that are present, the most massive object that is present of these three objects, M3 is the most massive. M1 is the least massive. They are both pulling each other. This guy, it doesn't matter if he's the size of an aircraft, he ain't going down. He's not going to fall through the table. We're going to say the table's so straight. He's not going to fall through the table. He doesn't contribute to any motion. But his mass creates an issue as far as the acceleration is concerned. You won't be able to accelerate as well because there's a third mass there. Just because there's no friction here doesn't mean this guy doesn't affect things. He does. If this was absent and you just tied the two ropes together and the M2 was absent, there'd be greater acceleration because not as much mass is being moved. Not as much mass is being moved. So it does mean something. Well, anyway, this guy, I don't want to draw too much of this stuff because it could be an issue, but maybe this will explain something. There is a force right here. I'm trying to think exactly how I want to say this, guys. There is, in the motion here, this guy's pulling up this way. As he is pulling up, as somebody's pulling him, somebody's exerting a force T1. Something's exerting a force of T1 right here. A force of T1 going upward is being pulled this way. If you yank hard this way, if I pull something this way, my shoulder's also experiencing a force the other direction. That's like the shoulder. In other words, if this was a car, and you tied a rope onto the car, if you pull this way, if you pull this way, or this thing pulls, there's a counter reaction. This guy pulls this way, and this guy yanks backward. He yanks backward this way. This pulls this way, but there's a counter. This is Newton's third law. It's easier said than explained, I think, sometimes. But I think the way you want to kind of look at it, I think maybe the best way to look at it is, if there's a pull right here, I don't want to draw too much though, because I think it's going to be a real mess. But if the arrow was the arrow's this way, you're yanking this way. If you're pulling this way, this guy's got to experience the fact that somebody's trying to pick him up. And he gets pulled that way. That's the action-reaction. And that's the same thing going on here. That's the same thing going on there. Now look, there's a pull upward, there's a pull downward. This guy's stronger than that guy because there's an acceleration upward. That means this guy wins. If we do a tug of war and we're at a dead heat, either we move at constant speed one way or the other. Let me not go through that scenario, but we could. There'd be no acceleration. Or we ain't moving. If we're in a dead heat, most of the time we're not moving. If there is motion, you can argue whether or not that's an acceleration anyway. I don't want to get into different word games we could play here, guys. Basically, if we're doing, for our purposes, if you and I are doing, me and someone else, or you and anyone else, you're doing a tug of war, and you guys are exerting the exact same force, but in opposite directions, you ain't moving. There's no acceleration. Could it be constant theoretically? Could there be a constant velocity? Yes. I'm not really going down that road right now. But I am going to say there's no acceleration for sure, and we'll say you're not moving. If we exert equal but opposite forces on an object, If we're tug of warring, the rope ain't moving if we're both exerting the same force on it. If we're both pulling in opposite directions with the exact same force, the flag that's on the rope is not going to move. T1 has got to be bigger than M1G. Why? Because there's an acceleration upward. There's a tension here, whatever it is. There's a tension here, whatever it is. This one's got to be bigger than that one. Why? Because there's an acceleration to the right. Just like T1 had to be bigger than M1G because there's an acceleration upward. There's an acceleration to the right. T2's got to be bigger than T1. M3G has got to be bigger than T2. Why? Because it's going downward. It's got to be bigger than that one. T2 is as big as this T2 because if I'm pulling this thing upward, I'm also getting yanked myself. If we got a rope and you're, like I said, we're both holding on the rope really hard, we're not going to let go. If I yank really hard, you end up coming toward me. Yeah, but I end up coming toward you a little bit too. And that's what's going on here. If somebody yanked this guy really hard, this guy got yanked. This guy yanked really hard means that guy got yanked that way, the same amount. If 100 newtons of pull was exerted right here, if you yanked really hard, you also pulled that way. If you yanked really hard, you also got pulled that way. If we both are holding on to a very strong rope and we don't let go, if I yank really hard, you end up coming toward me. Yeah, but I ended up coming toward you a little bit too. And that's all this is. You got yanked that way, you end up going toward the person, but the person ends up going toward you. Yank this way, going toward the person, yeah, but the person ends up going toward you. And that's where this is. It's a pretty big point. Well, these are huge, guys. These are huge. You've got 1, 2, 3. 3 important scenarios there. What is going on? Well, I got to ask you something. Maybe didn't talk about it as good as I could have. Does everybody understand that force equals mass times acceleration? Yes. Resultant force equals mass times acceleration. For scenario 1, what's the resultant force? For scenario 1, the resultant force, see, once you draw these circles, or these geometric objects that kind of look like circles or ellipses, once you've isolated all the forces, ladies and gentlemen, you can stay right here and talk about right here. Then you can go right there and talk about right there. Then you can come over here and talk about over here. As though you can pretend nothing else in the universe exists other than this. When you're done with that, nothing else in the universe exists other than that. When you're done with that, you can pretend nothing else in the universe exists other than that right there. You can treat, once we've isolated all the forces, you guys, once we've accounted for all the forces, you can treat scenarios. You can treat scenarios 1, 2, and 3 separately. What's the resultant force? Guys, didn't we say that this guy is stronger than that guy? T1 is stronger than M1G. Yeah? Really? Yeah, sure. If I do the subtraction, he wins. What happens to M1 if T1 is stronger? Oh, M1 gets fired upward. This difference right here, is the net force, the resultant force. The resultant force is M1 moving with acceleration A. The other one, scenario 2, is saying T2 minus T1. T2 minus T1, there's a tug of war. T2 wins it by how much? Well, M2A. This guy gets fired down. Everybody's moving. See, this guy right here, at the end of the day, has got the net force is, I don't want to write it, I'm kind of debating with myself how to want to write this. We know that M3G minus T2 results in MA accelerating, results in M3 accelerating. Why is everybody accelerating with acceleration? Why is everybody accelerating with acceleration A? Because they're all tied together. They're all tied together. And I got this in your notes, guys, but this is what's going on. This is what's going on. This is huge. This covers a lot of stuff. Later on, if we want to put friction in there, maybe we will. I don't know. We'll see. Let's see how this proceeds. Let's do this particular problem as is, and we'll take it from there. But you look at this, and it's looking something like that. This is it. Believe it or not, guys, this solves the problem. A lot easier than you think. Is there a way out of this thing? Yeah, I got an idea. If all that is equal to all this, and all that's equal to all this, and all that is equal to all this, so if this equals that, and this equals that, if this equals that, and this equals, if this equals that, and this equals that, and this equals that, then add all of this together, M1A, M2A, M3A. Wait a minute. That's M1, M2, M3. You could put I could factor the A out of there, and I did that. When I'll add the left side of all three equations. Then add the right side of all three equations. Be careful here. T1 and negative T1. Let's see what we got. T1 and negative T1 is 0. T2 and negative T2 is 0. You got M3G plus a negative M1G. What's going on here? Makes sense to me. Look what happens here, guys. M3G is the weight of M3. M1G is the weight of M1. There's a tug of war. This guy wins by M3G minus M1G. That's the unbalanced force. The unbalanced force equals total mass times acceleration. Pretty fascinating. That's like this. Mass times acceleration equals resultant force. Isn't the big weight minus the small, because they're both pulling in different directions, isn't the big weight minus the small weight a resultant force? Sure is. Isn't all of this the mass of everybody together? Yeah. Force equals MA. Force equals MA. So we got this. A is equal to. I mean, there's a lot of ways to write this. We're not going to, we don't have to beat it up too much, guys. I mean, we know we can do it. There it is. How do you want to find the tensions? Tensions are pretty easy. I can go back up here. I can do it a whole bunch of ways, guys. Once I get the ball rolling, I can do a lot of stuff. Tell you what I'm going to do. I can go right here. I tell you what. Let me solve for T1. Let me add a positive M1G on each side. Go right here. Let me add a positive M1G on each side, and I solve for T1. That becomes M1A plus M1G. M1A plus M1G, I can write it as M1A, M1G. I can write it like that. A little shorter way to do it. T2. Why don't you add a T2 on each side and subtract an M3A? Just solve for T2. M3G minus, it's M3G minus M3A. M3G minus M3A just like here, it was M1G plus M1A. Yeah, you can write it like that. It's no big deal. Well, that's how you can get those two. I wish we were here in person, guys. If there was a big room, we could just go for it that way. I wouldn't have to erase as much of this stuff, but we got this. We got this. We got the three of these things. I think it's going to work out pretty good. And that's how you do something like this, though. See what we can say here. I mean, it's kind of at that point, it's kind of a choice. Okay, and there's a number of ways to write this stuff. Always a number of ways to write this stuff, guys. So there it is. So what do you want to do? I mean, at that point, I mean, there's a lot we can do. Let's go. Let's put some numbers in here. Let's figure out what we want to say. A equals M3, which is 8 kilograms, M1, which is 3 kilograms, over the sum of all these guys, which is 3, 5, and 8, times G. The acceleration there, when you play the game, that's 5 over 16. That's 0.3125 times 9.8. It's going to be about 0.32 or something like that. Let's see where it comes out to on acceleration. Or not quite. Actually, not. It's going to be smaller than that. 0.3. Yeah, right. Exactly. 0.3125 is going to be less than that, actually. So it came out to this. 3 point. You understand. Yeah, that's it. There's your acceleration. Wow, it's a lot less than 9.8, isn't it? Yeah, you want 9.8? Well, let me do something for you. Let me take a scissors and cut this. If I cut this, there's no tension right here. M3G equals MA. The acceleration is G. If I cut this right here, there's no tension. There's no tension T2. If I cut this right here, T sub 2 is 0. It's a free fall. And it becomes A is equal to G. If I cut it right here as well, bam, there's no tension T1 picking this guy up. He'll fall straight down. If I cut both ropes, there's nobody powering this thing. That ain't moving. He ain't moving. He'll end up going 9.8 meters per second downward. He'll go 9.8 meters per second downward, and he ain't moving. But when they're connected, yeah, there's all this pullback. You got T2 pulling back, T2 pulls back strong enough, you ain't falling at 9.8 meters per second. T1 is pulling strong. It's got to overcome this guy, but it's not as though he can move. There's no free fall here, so it's a bit of a different situation. But you get the picture, you guys. You got to look at everything. Guys, this stuff ain't bad. What's T1? Well, isn't M1 equal to 3? Isn't this 9.8? Isn't this 3 point something? This is, this right here, this 9.8 is almost 10. This 9.8 is almost 10. This is about 3. 13 times 3 is about 39. All you got to do is plug in the stuff, guys. Let's see what we got here. You plug in. You go 3.0625, 3.0625 plus 9.8, get an answer, then multiply by 3, it's about 39. Man, T2 better be bigger. Why is that? Because this ain't moving. This guy right here ain't going to move unless the tug of war is won by T2. Take 9.8 minus 3.0625 and get almost 6.8, whatever, times 8. It's a pretty big number. 8 times 6 point something. It's going to be in the ballpark of 50. It's 53.9. Ladies and gentlemen, those are the 3 questions that are being asked of you. Those are the 3 questions being asked of you. What is the acceleration? What's the acceleration? What's T1? What's T2? T2's got to be stronger than T1. T2 is pulling the mass that's on the table, M2. T2 is pulling as a result of the tug of war. T2, T1, the result of that tug of war is the mass M2 on the table is getting pulled to the right. This guy pulling to the right, this guy pulling to the left. Here's this guy pulling to the right, here's this guy pulling to the left. This guy wins. 53.9 minus 38.6 is what? It's 15.3. Really? The tug of war? Yeah. What's 53.9 minus 38.6? That's 15.3. Why don't you take 15.3, the net force, divide it by the mass of mass 2. Mass 2 is 5. What is 15.3 divided by mass 3, which is 5? 15.3 newtons divided by 5 kilograms is 3.06 meters per second. Wait a minute. It's right here. Yeah, they better work out. It all works out. Okay? So that's the way it looks. That's the way it looks. T1 is 38.6 newtons. T2 is 53.9 newtons. Acceleration is 3.0625 meters per second. You got it. Great. What the heck? We're on a roll, sort of, right? We're on a bit of a roll, I guess you could say. What would happen if there was friction here? Let me leave a lot of that stuff up there. What does your gut tell you if there was friction there? Man, if there's friction there, this thing's probably, well, we don't know. Wait a minute. If there's strong, hey guys, let's get something straight. If there's strong enough friction between mass M sub 2 and the table, if there's strong enough friction between object M sub 2 and the table, if there's strong enough friction there, nobody's moving. Nobody's moving. Let's say the friction ain't that great and there's still motion going to happen. If there's motion going to happen, it's going to happen. You're not going to get these numbers, you guys. You're not going to get these numbers. What does your gut tell you? My gut tells me there's going to be acceleration, but not as big. My gut tells me there's going to be acceleration, but it's not going to be as big, and the tensions are going to be different. The tensions are going to be different. My gut tells me there's going to be more. Let me think. There's a lot of ways you can look at it. We'll have to see it, how it actually plays out. My gut tells me there's going to be more tension here. Why on earth would there be more tension here? There'd be more tension here because he's not going to let you fall down as fast. T2 is going to be a bigger number. It's going to be smaller. It's going to be smaller acceleration, but bigger T2 tension because it's not going to let you fall down fast. Smaller acceleration, and bigger T2 tension because this difference ain't going to be that big. You ain't going to fall down as fast. Okay. So it's going to be bigger that way, huh? This guy right here is going to be, it's an interesting point in its own right. It's going to be a smaller tension here. Why smaller? Because you can't pull this guy up fast. Acceleration is going to be smaller if there is friction. If there's friction, if I'm saying there's friction, there's going to be less acceleration than you would have had without friction. Less acceleration. Less acceleration means this guy is going to pull hard enough that you can't fall as good as you did before. T2 is going to be bigger if you got smaller acceleration. T1 is going to be smaller because he won't pull you up as hard. You say, well, wait a minute. If he's small and he's big, that should be a big answer. But you just said it's not going to be a big answer. Here's big, here's small. Yeah, I know, but there's also friction. The friction comes into it and it'll slow down the acceleration anyway. So that's what happens there. And you can see that. We'll see it when we can talk more on that. Is there mathematics we can discuss pertaining to it that'll get us there? Yeah, well, you see what I got initially here, how we played the whole game here. We've said a lot of stuff. We sure did, and we're going to erase a lot of stuff. Not everything. I'm not trying to erase everything here, but let's throw some friction in there. So this frictional force, you guys, is a contact force. I don't want to get into all the chemistry of it and all that other stuff. We don't need to start trying to develop that path. We just know that if there's a contact force like this, if I'm trying to push something across a rough surface, if I'm trying to push a refrigerator with no wheels on the sidewalk, or I'm trying to push a crate on the sidewalk, there's a lot of friction there. The force of friction, I'll call it kind of a cursive F right there. They write it differently in the book. Force of friction is directly proportional to the normal force times mu sub s or mu sub k. Mu sub s is static friction, if something is standing still or it's sliding. If you're moving it, if you got it in motion, mu sub k n. Now what's n equal to? N is called the normal force. N is if something's straight down on the table. Let's say here's the table. This is mass m. mg is straight down. The normal force is equal and opposite. The table exerts a force to not let this thing move. It's not Newton's third law technically. Newton's third law would be gravity and gravity. But for our purposes, again, that's another can of worms I don't want to open right now at least. We're just going to say that if mg is straight down, if nothing's breaking and nobody's falling and nobody's moving, if mg is the force straight down, the normal force is mg straight up. If something was sideways, like this, and this was theta, and we'll get to this. We'll get to this, at another time. If this is the mass here, guys, and this goes straight down this way, and the mass is mg, and the mass is mg. If this is theta, and this is 90, and this is 90 minus theta, a 90-degree angle here, this is theta again. So what happens here is, if this is mg straight down, this is mg cosine theta. And the table exerts a normal force equal to mg cosine theta. So the normal force is equal and opposite usually. It's not necessarily the case, but I mean it can be. It's not Newton's third law. It gets called that way sometimes on this one. It's not really. Newton's third law contributes to it, I guess you could say. So what we're doing is, so that's the thing. So the normal force here is this. So the more force that the table's pushing up against the object with, this is a coefficient of static friction. This is a coefficient of kinetic friction to make it move. This is what we care about, the movement friction. This tends to be less, a smaller number, because it's easier to move something once you've started moving it. Overcoming friction of something that's already moving is easier than if you start from a dead stop. So frictional force equals mu sub k times n. If something's just lying on the ground, F equals mu sub k mg. Again, guys, I want to make it clear. Like if it was this, and this was theta, this guy coming straight down, mg, that's 90 minus theta. How do you get the comp? If this is 90 minus theta, this has got to be theta. This is mg cosine theta. And n, equal and opposite force by the table, is mg cosine theta. Well, if theta is 0, if the thing is not inclined, theta is 0 and it's just mg. If it's lying on the table, mg goes straight down, mg pushes straight up. So this is the force of friction. Friction always opposes motion. Let's ask a question, guys. Let's get there. Help me out here, guys. If this is if it's here, there's a frictional force, F equals mu sub k times n. The normal force is m2g. Is m2g. We said the acceleration is going to go this way. Now what happens? Now what happens? Well, be patient with me, guys. We're doing extra here. We already solved problem number 47 pretty well. Now let's do a takeoff on it. Let's put friction into it. Do you understand, if the friction is, ladies and gentlemen, if the friction is great enough, nobody's moving. Forget motion. It ain't happening. If the object M2 on top of the table is massive enough, and if there's enough frictional force, these two guys pulling don't amount to a hill of beans. It ain't moving. It's not moving. So what are we going to do? Well, let's say mu sub k is not that much. It's easy to get this thing moving. It's easy to get this thing moving, and we'll figure out what's going on. You understand, if it's easy to get this thing moving, M3 being 8 kilograms and M1 being 3 kilograms, M3 has more gravitational force acting on it. So M3 and the gravitational force acting on M3 will power this thing to go to your right. It's going to go to your right. Can I ask you a question? Here's the crazy thing, ladies and gentlemen. Here's the crazy thing. T1 and M1G, subtract the two. The difference between the two is, the resultant force is M1A. Accelerate, M1A is the resultant force. Acceleration A, this guy M1 is going to go with acceleration A. This guy M1 is going to move with acceleration A. What does that mean? The unbalanced force is M1A. That's true. That was true before we put friction in here. M1A is the difference between T1 and M1G. Nothing changes, ladies and gentlemen. M1A equals T1 minus M1G. M1A equals T1 minus M1G. Period. That was the case before we had friction involved. It's also the case when friction is involved. In both scenarios, it holds. M1A equals T1 minus M1G. Let's go to this guy. I'm not going to do the middle stuff yet. Let's go to the other side. So the first one holds as is. So does the third one. M3G minus T2. I don't know what it's going to be. I told you it could be different numbers. But let's see what happens here. M3G minus T2, the difference between these two is M3A going downward. M3G minus T2 is M3A. M3A equals M3G minus T2. M1A equals T1 minus M1G. M3A is going to be the same as it was earlier. M3A is M3G minus T2. M3 and M1A equals T1 minus M1G. No problem. Here is the issue. Scenario 3 did not change at all with friction or anything. Scenario 3 did not change at all with friction or anything. Scenario 1 did not change at all with friction or without friction. With or without friction, 1 and 2 stay as is. With friction here, F equals mk m2g. Everybody almost stays the same. That's got to be put in there. That's the only thing you got to change. But it changes everything. The acceleration is going to be different. The tension is going to be different. Tension T1 and tension T2 will be different. Tension T1 and tension T2 will be different. The acceleration will be different. All for this one addition right here that you put on this thing. But everything else holds. This is if there's friction present. Pretty fascinating stuff in its own right. Guys, here's the moral to the story. The heavier the object that's on the floor that you're trying to push, the heavier that object is, the more difficult it's going to be for you to push it. If the object is half as heavy as it was in the initial situation, it's going to be half as hard to push it. If the object is 1/10 the weight that the other one was, 1/10, if it's the same kind of material, if it's 1/10 the weight that the other object was, 1/10 the weight will mean 1/10 the force. You'll have 10 times easier time pushing something that's 10 times less massive. That's 10 times less weight if it's the same material. That's where they're getting this from. It's directly proportional to mass. G is a constant, and then depends on the material present. What is going on here? This equals that, and this equals that. Why don't you add this, this, and this? M1A, M2A, M3A. That's M1, M2, M3. Just distribute the A out of there. Factor the A out of there, and you got this. Add these. T1 and negative T1 is 0. T2 and negative T2 is 0. Interesting. M3G minus M1G minus mu sub k M2G. Let's try that again. Add everything on the left together. Add this, and this. You got equations, so if this equals that, and this equals that, and this equals that, then this plus this is this. And that plus that is that. Let's confirm it again. T1 minus T1 is 0. T2 minus T2 is 0. M3G minus M1G. 3G minus M1G. And there's another minus, guys. There's that guy right there. U sub k M2G. Whoa! This guy makes it smaller. If he wasn't there, you'd have a bigger acceleration. The fact that he's there, he made it smaller. Acceleration. Let's see here. I can pull the G's out of all these. Let me not finish it just yet. Let me just kind of do something here. Put M1 plus M2 plus M3. Actually, please, no, let me finish it. Mu sub k. Guys, get rid of this for a second. And then you got your 3.0625 meters per second that we first had. Get rid of this guy, meaning no friction. Because you can't make this guy 0. There's no such thing as 0 mass. If we just said there is a mass, the mass is 5 kilograms. If this is 0, that means there's no friction. The bigger this is, the harder the friction is going to be to deal with for a given mass in a given circumstance. Get rid of this. M3 minus M1. M3 minus M1, the quantity M3 minus M1 over the quantity M1 plus M2 plus M3, that ratio multiplied by G will give you the 3.0625. 3.0625. Not now it won't. That's a smaller number on the bottom. That's a smaller number as a result. It's a smaller number as a result. If that's a smaller number, guys, if that's a smaller number, you could say, hey, wait a minute, Malus. You just said everybody was, these other guys, the very top and very bottom equations are the same as what they originally were. Solve for T1 and solve for T2, please. Right? Well, you remember that. Correct. And the other one is, you can say to me, Malus, what are you talking about? If these are the same, I should get the same answers. No, you won't. The acceleration is going to throw these off. We just said the acceleration is going to be a smaller answer. This was the answer you had before. 3.0625 meters per second per second. 3.0625 meters per second. Now it's smaller than that. Let's say it's, whatever, let's set it up in such a way it goes down to 2.5. Let's say mu sub k generated enough friction. Mu sub k is such that the answer is not 3 anymore. Let's say the answer was 3. It was actually 3.0625. Let's say now the answer is 2.5. Let's say the answer is 2. Let's say the friction was strong enough. Acceleration is no longer 3.0625. It is no longer 3.0625 meters per second. It's 2 meters per second. Why is that? Because this guy knocked it out. This is what it would have been, 3.0625 meters per second. Now it brought it down. This brought it down to 2. If it's brought down to 2, it's a different ballgame. You just put a smaller number right here than you had before. Smaller number, everybody else the same. T1's going to be smaller. T1's going to be smaller than what you had earlier. You had 38.6. Now you got something else. you know, you got, let me do the math. I'll just make it up. I mean, if this came out to, now with the friction, it came out to 2 meters per second per second. If that was the case. You know, whatever the math would be on that. What would T1 be then? 2 plus 9.8 is 11.8. 11.8 times 3. I just said this guy's 2. He's not 3.0625 anymore. He's 2. We said it was 2. Where did that happen? Well, something happened here. This right here made the math not be 3 something. It's just 2. This is 2 and this is 9.8. This is 11.8. 11.8 times 3. 11.8 times 3 is 35.4. T2. So the other one's going to be bigger. This is going to be smaller. The other one's going to be bigger. Let's compare. What's 9.8 minus 2? It's 7.8. 9.8 minus 2 is 7.8. 7.8 times 8, because M3 is 8, times 8, that's 6.4 plus 56. That's 62. Forgive me. No, let me see. 8 times 7.8, that's 56 plus 6.4, that's 62.4. Just doing this in my head, guys. What were they originally? We said this was going to be a bigger tension. He wasn't going to let them do as much. The original T2 without friction was 53.9. The original tension without friction was 53.9. Now it's 62.4. The original tension without friction was 38.6. Now it's 35.4. I made this up, guys, but I can make it work if I'd have to pick the mu sub k. We could sit down and work backwards. But you understand that. You understand. I mean, I'm not, you know, I wish people were in front of me. We could talk, we could make jokes and stuff. I'm not trying to insult anybody, guys. This is a positive number. This is a positive number. It's not as positive as this number, but it does make this result, which was originally present, this result gets smaller. This result ain't going to stay as big as it is. Why? That result's not going to stay as big as it was to get the 3.0625 meters per second squared. You lost some. How much? Well, you lost that much. That's the argument. That's the argument. That kills 2 birds with 1 stone. I think I've done this in other, there's probably some other places. I definitely have this in the notes somewhere. It's going to be provided for you on Canvas. But this is just something I just felt we needed to do, to look at it that way. Okay? That was 47. It's 47. Let's look at 68, and we'll call it on this one. There's number 67. Let me just see, make sure I got the right question here. What I intended to talk about to everyone. Not that, actually. I'm sorry. So that was 47 and then some. And then we did a whole bunch. We did friction and non-friction. 2 scenarios. You know, this one had friction before it was non-friction. Friction here. Friction here. Non-friction, just get rid of this guy. Makes a world of difference though. All three answers are going to be different in the two scenarios. T1, T2, and A are different, all different, in the two different scenarios as I've explained. If you're going to say non-friction, mu sub k equals 0. What happens if it equals 0? It's gone. The thing I showed earlier. With friction, it's that. And then do the mathematics. That was 47. And then some, as we said. 68. For problem number 68, a boulder of mass 80 kilograms rests directly on a spring with a spring constant of 6,850 newtons per meter. A, what is the compression of the spring? B, now instead the boulder and the spring are in an elevator proceeding upward at 5.19 meters per second. What is the compression of the spring in this case? Okay. So, got this in the notes as well, you guys. So it should be pretty straightforward. Let me knock this out for you, and then we'll call it on this one. I'll get into chapter 6 soon at another point. But let's get through this one. Let's leave this all in one place. I'm trying to make the videos a little bit shorter sometimes break them up. Sometimes it's nice to put everything in one place though sometimes too. So just watch what's going on. Let's see what we can do. All right, guys, what's going on here? There's a lot can be said about springs. I don't know if I want to talk about everything I could say on the springs. We're going to get into it in more detail, obviously, down the road. In the future, we'll get into more detail. For right now, vis-a-vis this problem from chapter 5, number 68. Basically, guys, there's a lot that goes on. I mean, they usually write Hooke's law, spring constant. It's similar to a lot of stuff we see. The spring constant they get its terms of magnitude is k times x. K is a constant. K is a constant. X is the amount of displacement. They usually talk about these things called ideal springs. And in an idealized spring, it's like a mathematical object that helps us do a lot of good mathematics pertaining to springs. Here's how they work. Regardless of whether I compress, let's say there's a huge spring that I've attached to a wall that can't move. And let's say I'm strong enough to compress. The spring has the property of being difficult to compress and difficult to stretch. Equally difficult to compress and equally difficult to stress. Equally difficult to stretch, equally difficult to compress. What does that mean? If I'm going to push on the spring and compress it by 1 meter, it's a pretty big spring, let's say. If I compress it by 1 meter, the amount of force that I have to hold it there in that 1 meter position is the same amount of force as I would have to have if I pulled it outward from the equilibrium position. So it kind of, there's a lot here. There's a lot here, and I guess we can debate what the heck we're going to do. It is a variable force. Right now at x equals 0 is what I got. If I compress it, delta x, and sometimes they call it x or delta x, whatever. If I compress it an amount, delta x, or stretch it an amount delta x, if I have to use 500 newtons of force to hold it out here, I also have to use 500 newtons of force to keep it compressed. It is just as hard, 500 newtons worth of force, to keep it compressed as it is to keep it compressed 1 meter compression. I've compressed it by 1 meter. Let's say I compressed it 5 meters. I compressed it by 5 meters. 500 newtons I have to hold to keep it there, to not get thrown backwards. If I pull it out 5 meters, I have to hold it there with a force also of 500 meters to hold it there. That's what an ideal spring does. Do you understand that the more you compress something, the more force you have to exert to hold on to it? If I compress it very, very much, and we're assuming this spring doesn't get weak ever, doesn't get ruined, nothing like that. If I compress it very, very much, it takes a lot of force for me to hold that spring in place. If I compress it half as much as I did initially, I only need to hold it with half as much force. If I compress it with 1/10 as much force as I did initially, I only need 1/10 the force. It's easier for me to start pulling the bow and arrow than it is. Let's say it's an old, some kind of bow and arrow that's not a compound bow or anything like that. Let's say I can pull, you got to pull it, and it's strong enough to hold you. It's easy to pull the bow initially, but to pull it all the way to the back is the most force. So it's a variable situation. The magnitude of the force depends upon how much delta x has occurred. Delta x is the same as x if you choose to have it that way. X is the amount of the absolute value of the displacement. They almost always write it like this. Force is equal to negative k times x. They use negative k because it always tries to restore what you've done. If I go in the negative direction, a negative number times a positive k is always positive. If I go in the negative direction, a negative number, so we can just say x equals 0 right there. Let me just say x because I'm using x right here. Doesn't matter, that's not a big deal. But as long as you're aware of it, if I go a negative 5 meters that way, negative times a positive times a negative, if this is positive, put a negative in front of it, it's negative. Negative times negative is positive. If I go this way, what does the force want to do? It wants to push me back toward the equilibrium position. It wants to push me in the positive direction. So if I go a negative x, the force is positive because it tries to push me in the positive direction. If I go positive x, the force is negative because it tries to restore me back toward the negative direction, toward the equilibrium. That's why they write this. I got rid of the negative symbol here just to tell you the magnitude is kx. Later on, we're going to talk more about this. We're going to get back to it and talk more about it. But right now, we'll say this. Now, they're saying here, a boulder of mass 80 kilograms rests directly on a spring with a spring constant of 6,850 newtons per meters. What is the compression in the spring? Instead the boulders and the spring are in an elevator going upward. What is the compression of the spring in that case? Okay, I got to talk to you. Do you understand that the weight of the boulder tells you how much compression there is? F of the spring equals F of gravity. Simple as that. Divide by k on each side. $80 kilogram boulder, 9.8 right here. K is 6,850 newtons per meter. Make sure all the units are right, guys. What is that? Well, for A, 68 times that, 8, it's going to be 8, it's going to be 784 divided by 6850. Let me see here for sure. Yeah, right. 784 divided by 6850, it's going to be for A, 0.114 meters. B, what's going on if you're going up in an elevator? If I'm going down with the elevator and the elevator is accelerating, I'm going to feel lighter. If I'm going up, I'm going to have a hard time standing up. We've noticed that. When you're carrying a bag of groceries, and everything's fine, you're walking fine, and the bag's about to break, the last thing you do is accelerate upward. You're putting more force on the bag. The last thing you do is yank upward. When the bag is starting to break, the last thing you do is pull upward, because you don't accelerate upward because you're putting more force on the bag. What do? You fall. You fall. There's less force on the bag. So if you're falling, it's going to be less, but if you're going up, it's going to be more. And that's where this is coming in. The Kx opposing this thing is going to be the weight of the object. That's what we had earlier. This is what we solved earlier, right? It's the weight of the object plus mass times the acceleration. The fact that you're accelerating upward means there's a normal force being exerted on the spring. The spring is accelerating toward the mass, which means there's going to be more compression. It's looking like that. X equals there's 80, there's 9.8. The elevator's accelerating upward. Yeah, I mean, our common sense tells us if it's yanking upward, man, there's more force on that spring. More force on that spring means that spring's going to get compressed more than it was earlier. More than it was earlier. .175 meters, as opposed to when it was just standing still. This is when it was just standing still, you guys. This was just the Kx equals mg. Standing still is this. You end up getting that when you solve it. Accelerating upward with the elevator is that. If the elevator was going down, you'd put a negative on there. It wouldn't compress as much. It'd take a lower. Hey, the bag of groceries is going to break. Oh, I better go down. It's not as much force on it. Not as much force. Not as much stretch on the bag. But this was going up. This is going up. Okay, you guys. That was chapter 5. That's quite a bit, but it's going to help you guys out, okay? Good to see you guys, and I'll see you guys soon. Bye.